Hello all, I'm Naren from School of Chemical and Biotechnology, SASTRA. This is a short video lecture as part of the Chemical Engineering Thermodynamics 2 course. We are in lecture 15 and part 5 on chemical reaction equilibrium topic. In this short lecture, we will just see the expression for equilibrium constant and how it is related to the activity of the component given by AI. Now, what we saw in our previous lecture is the criteria for reaction equilibrium. So the criteria for reaction equilibrium, we saw it as sigma mu I into chemical potential mu I is equal to sigma of mu I into Gi bar equal to 0. The chemical potential can also be written as a partial molar Gibbs energy. And then we saw by application of the definition of Gibbs energy to fugacity, we can establish the relationship that minus delta G R naught is equal to RT ln Ka, where this term denotes the standard Gibbs energy change of reaction, and Ka denotes the equilibrium constant, right? And this Ka is defined as the product of as the product of fugacity of the component in a reacting system to that of fugacity, the pure component fugacity at a standard state, and raised to the respective stoichiometric coefficients. So this is what we saw. Now what we are going to see in this lecture is the expression for this in terms of AI. So AI, which is the activity of a component I, is defined as fugacity of a component in a solution. So this is fugacity of a component in a solution to its own pure component fugacity. This ratio is called activity. Now just a small thought here, don't confuse this with the activity coefficient. So gamma I, this is the activity coefficient, right? Activity coefficient is defined as fugacity of a component in a solution, but here the reference is the fugacity of a component in a solution that is in an ideal state. So that means if you use here the Lewis-Rendell rule, here this denominator becomes xi fi, and then if you use the expression of AI, the definition of AI, this becomes AI by xi, or one can write activity is equal to xi times the activity coefficient. So that means we can say that activity of a component is proportional to its composition, and the constant of proportionality is the activity coefficient. So we have two terms, one is the activity and another is the activity coefficient. The activity, in both the cases the numerator is the same. In both the cases the numerator is the fugacity of the component in the solution, but in terms of activity the reference that is being taken is with respect to the component's own fugacity, whereas in terms of activity coefficient the reference is taken in terms of the fugacity of the component in an ideal solution. So this is comparing solution to that of a solution if it was ideal. This is comparing the behavior in a solution to that of a pure component behavior. So this is between a solution and a pure component, whereas this is between a solution and an ideal solution. So the scale of comparison is different in these two terms. So we are now using this activity. So this is how activity is defined for a component. So if you use that, now in the expression for equilibrium constant, Ka becomes, if I write Fi cap divided by Fi naught. This is just to denote the temperature scale at which the pure component fugacity is defined. This raised to the stoichiometric coefficient will become product of this Ai raised to this. I'm not just putting here not, but it is understood in both these cases it is at standard state. So this is at standard state. This has to be defined. So this is a generic expression. This is a generic expression, but in the specific case, when dealing with the reaction equilibrium, we are just writing the pure component fugacity at its standard state. So that means this is at a measured at a standard temperature and pressure, right? So the temperature and pressure at which the fugacity reference is taken is what is to be noted at this juncture. So this then means for a component, like say for example, if you take a reacting system as AA plus BB, this is how we are used to write in process calculation and reaction engineering, but let us use component index, because if we use A also for stoichiometric coefficient, then it becomes tough because we are already defining AI as an activity. So to make sure that there is no ambiguity in use of expression, I will write this as stoichiometric coefficient of the first component. This is stoichiometric coefficient of the second component, third component, and the fourth component. Obviously this is minus, so you should remember the stoichiometric coefficient is minus A. Here it is minus B, this is plus C, and this is plus D. So this is the first component, this is second component, this is third component, and then the fourth component. So if you apply to a 4-component system, let me just show how to write an expression. Sorry, excuse me. So this symbol denotes that it's a product. So I raised to the stoichiometric coefficient becomes A1 raised to its stoichiometry, A2 raised to its stoichiometry, A3 raised to its stoichiometry, and A4 raised to its stoichiometric coefficient, which on rearranging, you know that the stoichiometric coefficient of the first two components are negative, so it will eventually come A3 raised to C, this is A4 raised to D, whereas A1 will be raised to A in the denominator and A2 raised to B in the denominator. So that eventually shows that it is product of activity of product species, and here it is the product terms of activity of reactant species. So this is how the equilibrium constant gets defined. So equilibrium constant can be written as the ratio of a product of activity of the product species in the reactants raised to their respective stoichiometric coefficient to the product of the activity of the reactant species. This is also raised to their stoichiometric coefficient. That is how we write in here. I also want to just take a quick clarity on the term, how the summation of a log term gets changed. So this is what we did in the previous lecture. Sorry, this is a stoichiometric coefficient gets changed as ln of product of this term raised to the stoichiometric coefficient. We will, instead of writing this complete term, we will just write as an activity. So instead of writing this complete term, we will, if you denote by activity, this expression becomes sigma of ln ai raised to their stoichiometry, which essentially means, like say for this reaction system involving 4 components as we shown, so we can write it as ln of a1 raised to the stoichiometry of the first plus ln of a2 raised to the stoichiometry of the second component, ln of a3 raised to the stoichiometry of the third component, and ln of a4 raised to the stoichiometry of the fourth component. Now you know that the law in the long term that you can take product, so that means this would become a1 raised to its stoichiometric coefficient, a2 raised to its stoichiometric coefficient, a3 its stoichiometry, and a4 raised to its stoichiometric coefficient. So that means by using the algebraic product rule principles of logarithms, we can convert this summation to a product, and this is what we write as ln of the product notation of the activity of a species raised to their respective stoichiometric coefficient. So this is why I said that summation of a log is equal to log of a product. So this transforms summation of log terms to equivalent as log of the product terms, right? So with this we will come to the end of this short video. So what we saw is equilibrium constant Ka as the product of activity of a species raised to their respective stoichiometric coefficient, which means it is the activity of product components, okay, the cumulative product of activities of each of their component raised to their stoichiometry to the activity of the reactant species, the reactant components raised to their stoichiometric coefficient. So this is can be written as, like say, AC power C into AD power D divided by A of the component A to A of the component B. With this we will end this lecture, and in the next lecture we will try to relate how to calculate AA, AB, AC and AD in terms of measurable properties. What we mean by measurable properties is either in terms of concentration or mole fraction, or in terms of number of moles. Only when we relate this to a measurable property, we will be able to do some computation. Thanks for watching this video.